Hi guys, Mr. Kane here.
Hi guys, Mrs. G.
You know, Mrs. G, ideally speaking, we would have less gas loss, right?
True, that is true. It would be nice.
But it turns out that from the text here, it looks like we're doing more gas loss?
Yeah, one more.
One more? Only one more?
Well, we had the four guys, and
Okay.
we had the combined.
Okay, so the four guys, and then we combined them.
And then we actually used the four guys to make up the ideal gas law for one set of conditions. Don't forget the
Oh.
guys and the combined were for two different sets of conditions.
Okay.
I got this sample, I just heated it up. Now what happens? This is the difference.
So the ideal is good for if I don't have a before and an after?
Right. The ideal is good for I've got this much gas at this volume. What's the temperature? Yep.
Okay, all right, so let's check this out. So far we've got Boyle, who says that pressure times volume is a constant.
It's the only one with an opposite relationship. Yeah.
Charles says volume divided by temperature is a constant.
Yep. Charles in Charge TV show.
All right, Lusak
Right.
says that pressure divided by temperature is a constant,
Right.
right? And Avogadro says that volume divided by number of moles is a constant.
Right. Because each one of those guys took two variables and found the relationship between those two variables. One variable changes, the other one changes accordingly.
And they've all got this constant in common.
Correct.
So if we combine these together mathematically, then all of a sudden, poof.
We get that equal to the same constant, basically.
But and there's a thing. There's a new thing here. R.
R is the constant.
Okay, but so PV over NT equals R. That's not the way that I know this. It's not the way it's in the book.
No, because for an ideal gas law, they gave us one simple computation with a constant, and they rearranged that
Okay.
and came up with what we call PivNert. Doesn't it look like PivNert?
Why do we call it PivNert?
Because it looks like a PivNert.
PivNert. Oh, I see that. You kind of have to read it, right?
Yes.
PivNert. Yeah, I see. PivNert.
Notice all the variables are in there: pressure, volume, number of moles, and temperature, and the constant.
Oh, and
R.
that constant's kind of a fudge factor, huh?
It's just that little adjustment they make. It's a ratio kind of a thing. Liter, atmospheres, mole, kelvins.
Oh, wow, it's got complicated units.
Yeah, it's got interesting units.
Well, let's take a look at it. So, this has very specific units, this equation, right?
Correct.
Pressures have to be in atmospheres.
Yep.
You just kind of said that when you were
Yeah.
telling me about R. Volume has to be in liters.
Correct.
Temperature must be in Kelvin.
Which we've been doing all along, so
right.
that's not hard.
That's been a rule, yeah.
Yeah.
And R is this value. It was a fudge factor.
Yes, the
Zero-
0.08206 liter atmosphere mole Kelvin.
Okay, all
So
right.
it's kind of like the amount it changes, if you will.
And it's got units like that because...
Your units are like that so that everything cancels beautifully and you end up with the units for the unknown variable.
Oh, okay. So if I've got three known variables, it'll eliminate three of those units and leave the one that I want.
Right, because the PivNert's only got four possible unknown variables. R is a constant, so you'll never solve for R. It's
Right.
done.
Okay.
So you're either going to do pressure, volume, number of moles, or temperature. And they have to be in very specific units to go into PivNert, and they have very specific units coming out from PivNert.
Which is why R has units of liters, atmospheres, moles, and Kelvin.
Yep.
All right, very good. And we got an example here, huh?
Yep. And if you read it, it's one set of conditions. It's none of this, did this first and got this volume, P1, V1. It's not that.
Yeah,
It's
P1, V1 equals N1, T1.
Nope.
So this is actually going to be quite easy, right?
Yep, straight up.
I should be able to just write the equation and then write things underneath them.
Write the equation, write
So,
everything in the right place,
PV
do the algebra.
equals NRT. I guess the hardest part about PivNert is knowing where to put the equal sign.
Yeah, and then rearranging it algebraically to solve for, what are we solving for? Temperature.
It looks like temperature here. So pressure, P, that's hopefully that's given to me in, you said pressure had to be in atmospheres.
It has to be in atmospheres, so if it's not,
I see it in kilopascals.
You gotta
101.3.
convert it.
Hey, look at that. That's 101.325
Oh, yeah.
kilopascals. That's easy.
Yeah.
That's exactly one atmosphere,
You don't even
right?
have to grab your calculator for that.
1.00. The volume should be in liters, you said, and it is, so 2.70 times 10 to the 6th. Number of moles, they gave that to us in moles. That's nice. I guess they could have given it to us in grams. By this time in chemistry, we all know how to do that.
Yep, divide by molar mass. Ooh, that's a lot of moles.
Yep, okay. All right, 1.10 times 10 to the 5th, that's a lot of moles.
Yep.
Times R, which 0.0, I've forgotten already. What did we write
Well, 8206,
Right, and then we're multiplying by temperature, right?
Yes.
T is the variable we're looking for. So if I was going to do this, I would, well, 1 times 2.706 times 10 to the 6 is 2.70 times 10 to the 6.
Yeah.
So I would divide both sides by this
Product?
combined product.
And I get, now, since you're looking for temperature, and R is liter, atmosphere, mole, Kelvin, Kelvin's going to come out, or temperature is going to come out in Kelvin.
Temperature's going to come out in Kelvin. Gotcha.
299.
299. So you can even get this for 299 Kelvin.
299 Kelvin, because 3 sig figs, because of the numbering. Now,
Right.
they also want it in degrees Celsius, so it's going to be 299 minus 273.15, and using the rules for adding and subtracting significant figures, 26 degrees Celsius.
Oh, that's right. Ones place, right?
Yep.
Yeah, because ones place is
Yep.
the largest over here.
That's going to be the biggest issue, students, is the temperature and remembering the adding, subtracting of sig fig rules.
Right, so you might want to go back in your notes and review that real quick.
Yep.
That's first semester notes, isn't it?
Yes, it is.
Okay. This doesn't look too hard.
No, it's not.
It's as easy to do as Pivnert.
Yep.
Should we do another one?
Yes.
All right, so I'm going to do this again. PV equals nRT. And again, I know to use the Pivnert equation because there's only one set
of conditions. Now, can you do me a favor, Mr. Kane? I usually like to manipulate the actual calculation. Could you change that around algebraically to solve for pressure?
Sure. Let's see. If I'm solving for pressure, I would divide both sides by the volume of the gas.
Correct.
So I would get, so I'm going to write it over here. Pressure is going to equal nRT over volume.
Now, make sure, make sure everything's in the right units and plug it in.
Okay, N should be number of moles, so it should be 1.50,
All right.
and that's in moles, so that's okay. R was 0.08206.
All right, now temperature.
Temperature's not in Kelvin, so I've got to add 273.15 to that.
And this, since it ends at the since it ends at the
10th place.
10th place,
So I need 10th place.
306.2.
306.2 Kelvin, and that's going to wind up being divided by the volume, which is in liters, which is what I needed it to be, so divide by 21.
1.79, and units of atmospheres because of R.
It's in pressure, yeah. 1.79 atmospheres. All right. That's interesting.
And it's so easy, because now you don't, I mean, it's just kind of you can't compare it to anything. It's just kind of a plug and chug. Plug the numbers in right. So easy.
All right, that sounds good. I guess that's over.
That's the ideal gas law.